Okay, so we left off on an overall neutral solution. It has to factually always be that the charges have to balance. By the way, everything's 1, 1, 1, 1 here because of the fact that these are all 1 and 1 when they split apart. There's no one of those that gives two ionic species. For example, you could have had something like magnesium hydroxide, which would have been Mg2 plus over here, and then you would have had two OH minuses over here. Or another way of saying it is you would have had an OH minus concentration that was double this concentration. You actually don't need to express it either way, per se, but whatever. Anyways, you always have the charge balance. Negative charges have to equal positive charges. The other thing is, every time you have a chemical formula, that indicates some sort of mass balance. So for example, the only source of sodium in your solution, so the only source of the concentration of sodium, has to be that formal concentration of NaOH. So whatever the formal concentration of NaOH is, that would be composed of the different forms of sodium in your solution. In this case, because sodium is soluble in all of its form, and the only form it's going to carry in this solution is Na+. You won't have any other form, and so the formal concentration of the NaOH, which would all be all of the concentrations, is the same as the concentration of sodium. The formal concentration of HOBr, which is this concentration you would get by taking these moles here and dividing it by the liters there. Well, that has several different forms that it could be in. It could be HOBr, but it also could lose its proton and you'd be left with OBr minus. So your acid, uric acid, exists in two forms in solution. It exists as the weak acid dissolved in solution and the conjugate base after it loses its proton. And you know that also has to be factual, right? What are the different species? Well, in solution you have your different species, and those totaled together, added together, would have to give you your formal concentration. That's by definition. So the last thing you know about this solution is Kas. You know Kas exist and you have those values. You know that Ka has an equilibrium expression, which is always products over reactants. And the products, the concentrations would be to their power, which would be their coefficient in the reaction. So you have these reactions, the concentration of OBr minus to the power of 1 times the concentration of H plus to the power of 1 divided by the concentration of the HOBr, again to the power of 1, would be the Ka. That's the equilibrium expression. That same thing exists for Kw as well. Remember that this is a pure liquid, and so it goes to unity, meaning it would go to 1, so you don't actually have to put that in the equilibrium expression. And that's Kw, by the way. It has a special designation. This would be 10 to the negative 14 if you're curious, or if you forgot. Okay, so once we get an appropriate number of these equations, specifically we need enough equations that we can have them start canceling each other out and give us our variables. So we look up here how many variables we have. 1, 2, 3, 4, 5, 6. So how many equations do we need? Well, we need more than that. So we need 1, 2, 3, 4, 5, 6, 7. Alongside the fact that we know the Kw and we know the pKa, this should give us enough problems that we can use them to solve each other and start knocking out variables. So what you need to do is you need to start solving for all of the unknowns. So we can start with writing a fractional composition equation for each of the acids and bases. This will be a very handy tool, and it's a good place to start on almost all these problems. It's a very handy tool that you can use to start relating these different equations to each other. and start substituting them into each other, so you can solve single variables. So for example, the concentration of the HOBr in solution would be the formal concentration times the fraction of it that remains as HOBr. Alright, so this value right here, this fraction of HOBr, there's a simplified form in your book that you can use. So the fraction that would remain as the weak acid, not broken apart, not dissociated in solution, is always the H plus over the H plus concentration plus the Ka. And all that really is a simplified version of the equilibrium expression solved out for most weak acids using the common assumptions we would always make. So it's just a simplified version of the equations we've already written out, really. Anyways, so we plug that in place of alpha, which is the fraction, and that would give us that this HOBr concentration, well, that's in terms of a formal concentration, which we have, and an H plus concentration, which is in almost every other one of these. And so that will make that much more convenient to deal with. Plus a Ka, right? And again, a Ka is again something we have. So it's a constant. What would be the concentration of the OBr? Well, it would be the difference, right? So it would be the fraction that breaks up, so it's that difference, times the formal concentration that we start with. And so again, there is in your book a simplified version, which would be the fraction that breaks up. Notice it's like an inverse of this. It's essentially, we multiply both sides of this equation to get the other, if you're ever curious. But anyways, so it's Ka over the concentration of the acid, H plus Ka. And again, we substitute that in place of alpha, and that will give us the formal concentration on the top here, equals that concentration of the OBr minus that dissociated acid, the conjugate base that gets made from the dissociation of this acid. So we can insert the fractional composition equations into our charge balance, along with our known values of Na plus and our Kw over H plus for OH minus. Note, this is going to allow you to have that charge balance. So he has this term right here. We can substitute that in. We have term now that relates the OH minus to the H plus. Really, that's just this equation right here, right? This is a constant. So if we divide one of these terms over, it allows us to substitute for the other. And this is a value we know because it's the formal concentration right there. So notice we're really using these two equations to substitute in here. So we can solve it, but these two equations are very easy to solve. Okay, so we've taken those, substitute all the terms. Now all of the terms are going to be in terms of Ka, which is a constant, formal concentrations, which are values we were given, and concentrations of H plus. And that's what we have right here. This is that formal concentration that we've generated up here, right here. This one is just the Kw relationship. Kw equals H plus times OH minus that we solved to get OH minus on one side. So we could substitute this in. Notice that this value is also a constant again. We have H plus concentration, which is nice because it matches all the others. And we have a value of the sodium, which was the formal concentration of the sodium hydroxide. So we can then set up a spreadsheet like the one that we are going to see right here. Essentially, all that we have to do is set up a spreadsheet so that we have these going into one over another, take an initial guess, and use the solver function, right? So again, we set it up with those formal concentrations, equilibrium constants that were given in the problem. We put that in. We go ahead and put an initial value of pH into a cell. In this case, this was H7 that you're using for that initial value of the pH. This is then going to be used as an initial guess. We would then let it solve. It would solve for that pH. And in this case, we just went ahead and put in, because I know what the answer is. Anyways, so the initial value of the pH, it would then solve. The sum of the charges would then give you 0 if it is correct, because that is the charge balance. All right. So you use the solver. It'll vary that pH until that charge balance equation gives you an overall 0 difference, so that the two sides are equal. Anyways, that's just solver. There's not really much more to say about that. You may need to let it do a fair amount of cycles to let it solve. Anyways, yeah. So the spreadsheet would then solve. You'd get a number approximately 0, and that would give you your values for each of these concentrations. Note that this concentration is actually a constant. You were given that value actually. These concentrations actually have to be generated, though it is ironic and somewhat funny that it, due to the fact that you did it with the solver, it will overestimate the accuracy of this number right here. But anyways, it doesn't really matter, I guess. It's not a big difference. It's only a factor of 10. You could theoretically solve this by hand. It would just be fairly difficult to do. It would take a lot of work because it's not a trivial problem to solve. The Excel solver will save you a lot of time if you figure out how to set that up. And I would use, before you try to do this, I would actually go, there is a sheet, well, I guess I have a sheet of formulas right here. So I guess you could set it up once and see how it works, and then do your own thing. But in your book, there's actually a sheet with formulas that, with like what each of the cells has in it. And that's why I would always recommend to figure out how to use the Excels. Set up the example sheet they give you first. See if you can do it and you get the same answer as them. It's following those steps. And then go back and do your own problems, okay? Anyways, let me know if you have any issues here. Again, you could do this either way and it would work. You can do it with the assumptions, in which case you'll solve everything. You'll get down to it, you know, the equilibrium concentration of this, and then you could just do a simple ice problem to figure out the H plus concentration, and that'd be it. Once you have the H plus, you can get OH minus and pH by just taking negative log of H plus, and then doing the 14 minus the pH would give you POH. 10 to the negative POH would give you the OH minus concentration. Anyways, either way will work. I would get used to doing the solver and get so you got that down really fast if you have the time, because it's actually very useful. But anyways, let me know if you have any issues or if you don't understand anything. I guess I can, well, I won't be able to do it this semester, but sometime I should do a video of that, doing the solver. Okay, you take care, and let me know if you have any issues.